In the previous class, we have make we have made use of Michaelson Moldy experiment. The result of the experiment is that the speed of light is independent of any inertial reference frame. The Michelson-Morley's original assumption was that there exists an absolute frame in nature in which the medium of the electromagnetic wave that is hidden in the vacuum, in which the speed of light is well defined, and the speed of light is independent of the direction of propagation. However, their final result was to disprove their assumption. Just like the reduction to absurdity, their assumption that there exists an absolute frame in which the electromagnetic field propagates with the same speed isotropically was wrong. Instead, the speed of light is always the same in any inertial reference frame. Albert Einstein made use of this result as the starting point his theory that is called the special theory of relativity. All of the formulation based on the Galilean transformation, although their final result was wrong, just by changing the way of thinking that the time may change depending on the frame of reference. Although the homogeneity of the flow of time is the same in any reference frame, there is an overall factor between the transformation factor when we make a transformation between the two inertial reference frame. That is called Lorentz factor gamma. The time tau is called the proper time. That is measured by making use of a clock that is fixed in a reference frame. Another time tau appears in a clock that is physically moving clock. This means proper time is the time only if something is not moving. That means the time gap between the two events that appears at a single spatial position. Only in that case we use the proper time. If there are two events that happens in different positions, then there is something, some massive particle moving from the initial point of measurement of time to the final point of measurement of time. The velocity connects this to equate the actual distance of travel. And this t is not equal to the proper time tau. Instead, this t is tau multiplied by gamma, and gamma is the Lorentz factor 1 minus v squared over c squared. And it approaches infinity as approaches the speed of light. And any massive object has its own rest frame. It can be boosted to go faster and faster and faster. Although you pour whatever amount of energy to that massive object, you can never reach the speed of light. That's the final consequence of the Michaelson Moldy experiment. We make use of this relation to find out the complete transformation rule for the space-time coordinates. That is called the Lorentz transformation. And what we have obtained for this formula, time dilation, is absolutely equivalent to the fact that there is a length contraction. This any moving object is contracted. The length of a moving object is always shorter than the length that is measured in a frame where the rod is at rest. The figure shows the two objects, the two rods. One rod is fixed in a frame as a star. The other is moving with a relative velocity v with respect to the rest frame. Let's see, there's a rest frame, and the other one is moving frame. In relativity, if we look at the lower bar from the bar above, actually this S is a rest frame, and S star will be the moving frame, and the relative velocity will be opposite, minus v. The magnitude is the same, but motion must be opposite. That is the origin of the name relativity. The relative motion is opposite to any one of a pair of jobbers. A look at B, B is moving with V. Then if B sees A, then A is moving with minus V. That is, a relative velocity is opposite. Okay. What we want to make use is the only formula that the time is like dilated when the clock is moving. One simple way to measure the length of a rod is using proper time. The simplest one is to fix a clock at A star. A star is the origin of S star. And you start the stopwatch and measure the proper time tau. Because you are at the origin of S star, what you see in the clock is the proper time. Because if watch is fixed, it only shows the proper time. But instead, the upper rod arrives at the origin, you start, and then this rod passes to the right, and this is the time when the left end of the upper rod arrives at the origin. So this is 0, and when it reaches the left end reaches this point, you will find the proper time tau. We make use of this proper time tau to measure the length of the upper rod. How? Just multiply relative velocity to the right. So magnitude of the relative velocity, relative speed is v. So v tau is the length of the upper rod. In this way, you can measure this. We have measured the length of the moving rod like this. And there is another way to measure the moving rod. We consider the motion of the right end position of the upper rod. We notice that this point is moving with the velocity v to the right. Therefore, the space-time coordinate of this point, because it is moving, we can write it as a ct and vt. We'd like to see what happens when this point meets the right end of the stationary rod. Because this position is not moving in the frame as a star, the time required to move this right end to the right end of the stationary rod is just Vt equals L0, because these coordinates, space-time coordinates, are written in the frame as the star. In this frame, the upper rod is moving, but the right end of the upper rod meets the stationary point with the coordinate L0. Finally, what we find is that the time t required to move to the right end of the moving rod to hit the right end of the stationary rod is t, and that t is L0 over v. Here, this is the time tau. Tau is L over v. Okay? We know this t because the moving object slows down in time. That means the time delays. We have time dilation, gamma tau. We just take the ratio of these two. Okay? Tau. We have gamma tau equals L0 over V. Tau equals L over V. So tau equals L0 over V equals L0 gamma and L over V. VV the same, so L0 over gamma equals L. L is the length of the moving rod. L0 is the length of the stationary rod. Gamma is greater than 1. So L, length of the moving rod, is shorter than the stationary rod. That's the reason why we say length contraction. And length contraction is closely related to the time dilation because we have used time dilation, only a single constraint of time dilation to reach the length contraction. This means this t is always greater than tau. That means tau is the time required to shift the left end of the moving rod to this position. That means this is tau. And the time t is the time required to move the right end to the right end of the stationary rod. This is t. This t is always greater than tau. That means this one must move long distance, L0. This length L, that is measured in the rest frame, this one must be shorter than L0 only if the case. Only if it is the case, t is greater than tau. That means because it is shorter, it takes a longer time to the right end to reach the right end of the stationary rod. Because it became shorter, the left end leads this position. Left end of the moving rod means the left end of the stationary rod earlier than the right one. This is the direct consequence of the time dilation. So length contraction is nothing but a consequence of time dilation. That is very, very important. So L0, we put subscript 0 to indicate an object that is measured in the rest frame. We call this one to be proper length. And proper length is the longest length of an object that is measured in any inertial reference frame. And as soon as it moves, the length of an object always decreases along the longitudinal directional motion. For example, if we have a sphere, if it moves with velocity v, and we have a corresponding Lorentz factor gamma that is always greater than 1. If v is non-zero, then the length, longitudinal length, the length along the direction of motion decreases from L0 to L0 over gamma. That is in this way. So, because of beta, which is V over C, the magnitude of beta is in this region. Therefore, gamma, 1 over gamma approaches 0 as beta, absolute value of beta, approaches 1. Then the length disappears. This is an example. When a particle is moving slowly, we do not notice the we do not notice the change in the shape. However, if it moves very fast, the longitudinal direction, length of the longitudinal direction is shrunken. In the limit, this is here, this is beta, and this is gamma. If beta is a 0.2, we cannot notice any significant modification of the shape, but if we reach beta is approaching 1, gamma is increasing very much, so L is L0 over gamma. This is a factor 22, is a very large number, so it becomes only 5%, less than 5% of the original diameter. It becomes very short. So the length contraction is the direct consequence of the time dilation. You can follow this calculation to find the exact review, a review of Michaelson Moldy's experiment in terms of relativity. The final result will show that the time has additional factor gamma, that this gamma is an exact factor of time dilation. Now, being equipped with the constraint of time dilation means any event separated, any event that has a time difference of proper time in a frame of reference must happen at the same position. I mean, if the point of measurement is invariant, what we measure in the time difference is proper time. This is measured in the frame where the clock is not moving. We can measure the same time difference in a different reference frame where the origin, here this origin is fixed, but this origin can move in another reference frame. In that reference frame, this origin is moving with the relative velocity v. For simplicity, we have chosen a single direction because the transverse direction perpendicular to the relative motion does not change the shape. Only the longitudinal direction is shrunken in the space. In that case, we have this kind of spatial, both the spatial and time separation of the two events. So what we want to find is the transformation matrix that connects the same space-time event measured in two different reference frames that are moving with non-vanishing relative velocity. We recall that in order to find out the rotational matrix, in three-dimensional Euclidean space. For simplicity, when we consider the two-dimensional Euclidean space, what we require is usually the invariance of vector squared under rotation. A point x comma y that can be rotated by an angle theta about an axis perpendicular to the plane and passing through the origin, and we will obtain the new coordinates. Although the coordinates are transforming, the distance r and r prime from that point to the origin is invariant under rotation. So this requirement under the rotation says there is a rotational matrix that relates the two coordinates in such a way that is completely determined by finding the transformation rule for a simple vector. For example, what happens if I rotate 1, 0? There's a unit vector along the x-axis by angle of theta. What I would get is cosine psi. If I rotate a unit vector along the y-axis, I would find this is minus sine theta, cosine theta. Just by choosing the two transformation rule that are linearly independent, we can determine what the matrix really look like. That is cosine sine and minus sine and cosine. In fact, this matrix is independent of the coordinates. So just we have made use of a very simple coordinates to determine the matrix. However, it works for any points in the space. Just like what we have done to determine the matrix elements of the rotational matrix, what we want to do is to find a simple relation and the principles of relativity to determine the Lorentz transformation matrix that connects the space-time coordinates from the rest frame. I would say the matrix lambda. What we want to do is to find out the explicit matrix or lambda that satisfies this constraint of time dilation. The constraint of length contraction is nothing but the constraint of time dilation. It does not provide us an independent constraint. What we can make use is just a simple a single constraint that the time dilation is evident experimental fact. And the second one will be the relativity. For example, if there are two observers in a frame of reference that is called SA and SB, if B moves with the velocity v, then to B, A is moving with the velocity of minus v, the same magnitude but opposite direction. What we want to make use is just these two constraints, principle of relativity and time dilation, that is confirmed by Michaelson-Moldy experiment. Okay, let us find out the explicit form of the Lorentz transformation matrix. Here I have summarized the constraint that we require. The length contraction appeared along the direction of motion, that is longitudinal direction, and there was no difference at all in the direction that is transverse to the relative motion of the two systems of initial reference frames. Hence, for the time being, let us ignore the direction perpendicular to the relative motion because that are invariant. So if we consider the transformation matrix, we first need to introduce a full vector, or vector is called the space-time coordinates. The zeroth component is the time, and there are three spatial components. A four-element vector is to be transformed from the rest frame to another frame. Here, we assume the direction of motion between S and S star is along the x-axis. Then, the two coordinates y and z are invariant. Y must be the same as y prime, and z must be the same as z prime. Here, in order to indicate the rest frame coordinates, we use star for the rest frame. All right. Thus, the matrix for CT, X, or Y, Z, the matrix do not touch at all for the transverse direction Y and Z. The only possible way is to put them one in diagonal elements and do not allow any interference coming from the other coordinates, T and X. Therefore, let us call this lambda, this 2 by 2 matrix. We are interested in the 2 by 2 matrix, transformation matrix, that is CT prime, X prime, is lambda CT X, or CT X from CT star and X star, whatever. And this matrix is chosen to be AB because c is the speed of light. We do not want to use c instead of PQ. We would like to identify these four elements. First of all, from the rest frame, C tau, if I multiply this transformation matrix, what I would get is a CTVT. If we divide both sides by C tau, what I get is T over tau and V over C, T over tau. That is Lorentz factor gamma and gamma beta. That should be obtained if I multiply A, B, P, Q. And because I have divided C tau, it is 1, 0. If I multiply 1, 0 to this matrix, what I would get is A and P. I can copy this. A must be gamma and P must be gamma beta. Therefore, what I get is matrix ABCD, ABPQ must be gamma. gamma beta. I don't know. I don't know. Okay. This is what I get. So from the raster frame, 1, 0, moving frame, I would get gamma, gamma beta. I'd like to know the inverse matrix. Inverse matrix, that means if I know the inverse, what I would obtain is gamma, gamma beta is multiplied the inverse. What I would get is 1, 0. Because this is by definition. Because 1, 0 is multiplied to lambda. What I get is a gamma, gamma beta, this vector. The next one, this one, what can I do? Let us recall the rotation matrix. Cosine theta, sine theta, minus sine theta, cosine theta. I can find the inverse. I can find the inverse of this matrix by substituting minus theta, or by taking the transpose, because it is an orthogonal matrix that preserves the scalar product in the Euclidean space. R theta's inverse equals R theta's transpose, and that is just inverse rotation is if I rotate in this way, inverse is just a backward. Simple. But I don't really know that I should do to find the inverse in the case of Lorentz transformation, because Lorentz transformation is absolutely different from ordinary rotation defined in the Euclidean space. Instead, Einstein says there is a relativity. That means if I want to find out the inverse, if I want to measure the velocity of the upper one, this is a v, then if I measure the relative velocity measured by s of this lower one, that is the same in magnitude, but that is that the direction is opposite. It's quite simple. Therefore, the relativity says lambda inverse is nothing but lambda, except that v is replaced with minus v, because everything between the two systems is the same, except that the relative direction of the relative velocity is opposite. Therefore, I can find that inverse should be the same as this, except that I replace v with minus v. Beta is v over c. So if I want to make an inverse transformation, the relative velocity v should be replaced with minus v. So this beta should be replaced with minus beta, that is minus v over c. Next, what happens to gamma? Gamma is 1 over 1 minus beta squared. Even though I replace beta with minus beta, the sign of gamma doesn't change at all. Therefore, the inverse matrix, I just copy this one. Gamma is the same, but I have to flip the sign of beta. But I don't know what they are, B and Q. Okay, let me call it B prime and Q prime. And B prime is the value of B, except that B is replaced with minus B. I don't know what B is. Q prime equals Q, except that we replace B minus with minus B. That's what I have at the moment. The first constraint what we have used is the time dilation. And the second constraint what we just have found is the theory of relativity. The relative velocity between two objects is the same in magnitude, but opposite in direction. So the inverse Lorentz transformation matrix can be determined in such a way. So why don't we substitute this matrix in here? And there are two constraints, and there are two unknowns, and it is absolutely possible to find those values. You can follow the simple calculation to find out what these values are. After substitution, what we get is this. It's a trivial calculation. I don't want to. You can always follow this calculation by yourself. Finally, what we will get for the matrix lambda from rest to the moving frame gamma beta. This is from C tau 0 to Ct Vt. Lambda inverse, just to put negative sign on it, so on beta. We have opposite sign in here. That is a relative. Let's see. Here, I use the different coordinates. Beta is defined in different way. The simple way is if the frame of reference goes backward, then a stationary object will move forward. Okay? The final result for the boost will be positive if the relative velocity is negative. If the relative velocity is positive, if it is moving forward, an object at rest originally will move backward. That's the difference. Finally, we can insert this kind of matrix and inverse matrix and insert the identity matrix that preserves the transverse direction. Transverse directions are invariant. All right. Therefore, if we make use of this relation, in this case, the boost is forward. Boost is forward, then the particle, stationary particle will move backward. So in that case, the lambda has the velocity dependence minus sign. Okay, so in that case, why don't we substitute explicit value for the components? Gamma minus gamma beta minus gamma beta gamma for the Ctx. That should be Ct prime x prime. All right. Gamma is always a factor that all four elements has a common factor gamma, and Ct minus beta x, and gamma x minus beta ct. We divide both sides. Ct prime equals gamma ct minus beta x. Divide t minus c. But beta is v over c. So beta is v over c squared x. And x prime, this is gamma, x minus beta c equals v minus vt. Finally, what we get is this transformation rule. Sure, there is y prime equals y and z prime equals z. You know, this gamma equals 1 over 1 minus beta squared. Why don't we take a limit as beta goes to 0? Beta goes to 0, that is a non-relativistic limit. Beta goes to 0, but just beta goes to 0 means v over c. Just to put v over c equals 0. But just to keep the v itself as it is, you know, v over c can vanish in the limit where v is much less than the speed of light. What we get is gamma goes to 1, and this one vanishes. So what we really get is t prime equals t, and x prime equals x minus vt. Transverse direction is the same. That is also true. What is this? This is Galilean transformation. Even though Galilean transformation fails for the description of very fast objects just like light, photon, it is still valid in the non-relativistic limit. Therefore, the relativity is not a special theory that absolutely ignores the Galilean transformation that we really know very well in the non-relativistic limit, in which an object is slowly moving relative to the speed of light. Therefore, this is a kind of correspondence principle, just like quantum mechanics. It must reproduce classical physics in the limit where classical physics is working very well. And the inverse transformation is mathematically it can be very complicated if you find out the inverse matrix for the 4x4 matrix. However, we know the relativity says the inverse can be obtained. Inverse of the Lorentz transformation matrix can be obtained by simply replacing this relative velocity with the same one, except that the sign is replaced. I don't know whether you are familiar with this or not, but you are well familiar with navigation, and that depends on the GPS system, geo-positioning system. And this geo-positioning system is not working well if we do not consider the special theory of relativity and the general theory of relativity as well. The error will be 10 kilometers, more than 10 kilometers per day. But if you drive, you need an error less than 10 meters. It is impossible to commercialize the GPS system if we ignore the theory of relativity. Okay, at this stage, it's better to review the invariant property in of the scalar product of three vectors on the rotational transformation. A Euclidean vector defined in three dimensions, sure, we can generalize it into n-dimensional Euclidean space. As far as our problems are concerned, we are satisfied with staying in the three dimensions. A vector is a linear combination of three components. On the rotation, these components vary. However, the scalar product with another vector, that is a1, b1, a2, b2, a3, b3. This is true only if we employ Cartesian coordinates. This is invariant on the rotation. Now, this is a constant, and if you take the scalar product, then the actual value that this vector rotates. Hence, a dot b is a1, b1, e1 hat, dot e2 hat, e1 hat, and so on. Among all 9 terms in these expansions, only the term with the in the summation ai, ei hat, b, j, ej hat, scalar product. This is non-vanishing only if I and j are the same. So the final result is a sum over I, as from 1 to 3 for ai, abi. This on the rotation, once the scalar product is invariant, the scalar product with itself, this is a square. We can also write in this form, square of a vector is also invariant. What we want to look at is the invariance of the scalar product and three vector. Three vector means a three component vector. Three component vector defined in the Euclidean space. 3 indicates the Euclidean. We have four vector. Four vector we have CT and x1, x2, x3. This spatial component of space-time event is this spatial component is Euclidean. However, we will find that this is a full vector that has index. To distinguish this one from the Euclidean one, we use the Greek index, and this Greek index runs from 0, 1, 2, 3. This 1, 2, 3 indicate the spatial component, and 0 component represent the time component. So the scalar product in the Euclidean space, three-dimensional vectors, are invariant under rotation. Especially in the two-dimensional Euclidean space, we can rotate a vector by angle theta. Then a vector, which has a1, e1 hat, a2, e2 hat. Rotation means we can rotate the basis vector, keeping this coefficient the same. So transformation rule can be obtained. This I don't have to explain this one very detailed because in y1 vector we have already studied enough. And rotational, the matrix representation for the rotation 2D rotational vector, rotation of the Euclidean vector is given in this way. Interesting point is that the rotation is usually in general non-commutative. However, if we fix the axis of rotation, then rotation can be done successively and we can change the order of the rotation as long as we fixed axis rotation. Fixed axis rotation, they commute. So in general, matrix product is not commutative. However, it is always true that associative law is valid. In the case we fix the axis of rotation, then we can change the order of rotation. The final result is always the same. So we rotate by theta 1, theta 2, and theta 3. Then rotation about a single axis is just the sum of the three angles, keeping the axis and hat to be the same. Therefore, if I rotate by an angle for n times, this is identical to rotate about the same axis by n times of angle. That can be verified in a straightforward algebra of the matrix algebra. The special feature of the rotation matrix is its orthogonal. That means if we write down the explicit matrix representation, every column or every row, they are orthogonal to. Any two of them must be the scalar product of any two rows or any two columns. Scalar product is zero if they are different. It is non-zero only when we multiply square a single row or a single column. In addition to pure rotation, the rotation matrix has every row to have unit normalization. In summary, if I multiply transpose of this matrix, what I would get is this kind of form. Only the diagonal elements becomes 1. And off-diagonal elements are all the scalar product of different indices. This is true for any case, E1 hat, E2 hat, E3 hat. Any unit vector in the Cartesian coordinates are orthogonal to one another. So I mean AI dot EJ hat must be canonical delta. That means it is 1 only if I and j are the same. And if it is not the case, it is always vanishing. Hence, the inverse matrix of, because this is identity matrix, inverse matrix of a rotation matrix is always the transpose. So we do not have to compute the inverse in a very complicated way. For example, we can make use of Kramer's rule to find the solution, but in the rotation case, what we want to do is just to take the transpose of this matrix to find the inverse transformation. Because of this, this is in summary, this is called the orthogonality. Every row and every column are orthogonal to one another. That means that is summarized in this way. This and transpose, if you change the order, it is always identity. Therefore, this leads to the conclusion that matrix inverse is transpose. This is the definition of the orthogonal matrix. What is orthogonal? Rotational matrix is always orthogonal. One more important point is we can compute the determinant. Pure rotation has always determinant 1 plus 1. And if there is a single reflection inside the transformation, that determinant becomes a negative sign. The usual pure rotation is always a determinant 1. And we consider a parallel pipe generated by, spanned by 3 linearly independent vectors. This volume of a parallel pipe can be computed A cross B dot C up to the signature. The sign can be determined. This is A cross B is along this direction, and that is on the same hemisphere, on the same half hemisphere, separated by the plane spanned by A and B, and this A cross B is on the same side as the C. Hence, this is a positive definite. So we can say A cross B dot C, the triple scalar product, is the volume spanned by these 3 vectors. On the rotation about the fixed axis and hat by an angle of theta, then every vector has the different components with respect to the original frame of reference. However, the relative angle is invariant. Therefore, the A prime plus B prime dot C prime must be the same. This one must be the same under pure rotation. Sure, if there is a reflection, then we have to include the additional phase factor that comes from the determinant negative sign. But pure rotation, it is always a positive definite. We recall that this triple scalar product can be expanded in terms of permutation symbol, that is a Levi-Civita symbol, and that is if we use the determinant, we can express this one in this way. So this overall vector dependence of determinant is vanishing. It becomes 1 for ordinary pure rotation. However, if there is a reflection, for example, x goes to minus x and y is y and z is z, still this one keeps this, x squared is x squared plus y squared plus z squared, and this one minus x squared plus y squared plus z squared. This square is also invariant. However, this transformation matrix is minus 1, 1, 1, this kind of form. This determinant is minus 1. So if we have an odd number of reflection in the transformation matrix, then we would get the determinant vector minus 1. except that in pure rotation, we do not have to consider this determinant factor. At the last stage, we consider the full vector in the Minkowski space. In comparison with the Euclidean space, we use the Minkowski space for full vectors. Phi means the XYZ components, and the 4 means time and XYZ components. Under rotation, an Euclidean vector rotates if it is origin. If we rotate a vector whose coordinates are x and y, it becomes a circle, and this radius is invariant. Although the coordinates x prime and y prime are different, hence the square of this vector is x prime square plus y prime square, and square of this original vector is x squared plus y squared. In the matrix rotation, this transpose x. That means is x, y row vector, x, y column vector. If I multiply this, x squared plus y squared. After rotation, it is x prime transpose x prime. That is x prime, y prime, x, y prime prime. So x prime squared, y prime squared. So Euclidean free vector, on the rotation, its square is always invariant. However, in the Minkowski space, this is a Euclidean space. Euclidean space is the space where the coordinates satisfy the Pythagorean theorem. X, y, r equals x squared plus y squared. Minkowski space, the scalar product in the Minkowski space is defined in such a way. We have 4 vector whose zeroth component and spatial components. We have 3 spatial components and a single time component. Sometimes we say the zeroth component and the first, second, and third components. If we square this, it is not the sum of the squares, but the difference. Zeroth component squares subtracted. This is quite important. Subtracted by the square of spatial components. And square of spatial components is x0 squared minus x1 squared minus x2 squared minus x3 squared. Because the 4 space-time event at the rest frame is c tau 0, 0, 0. If it moves along the x-axis with the velocity v, the space-time components will be ct, 3t, transverse is 0, 0, something like that. The square of this 4 vector defined in the Minkowski space is zeroth component, c tau squared, subtracted by the spatial component, 0 squared. In the moving frame, this is ct squared subtracted by 3t squared. This is the formula for the time dilation. As a result, still we consider a right triangle. However, the invariant one is not hypotenuse. This is hypotenuse. However, this is vertical side. This direction is invariant. And the coordinate transformation changes the shape of this ct and vt vary. However, this square subtracted by this square is always invariant, that is, proper time squared multiplied by speed of light squared. In general, scalar product of four vector is expressed in such a way. Scalar product of zeroth component, the time component product subtracted by the normal usual Euclidean scalar product of the spatial component. This is subtraction. This is the this is the big difference between the Euclidean space 3 vector and the Minkowski space 4 vector. If we ignore the transverse direction and consider only a longitudinal direction, x direction, then the Minkowski 4 vector can be expressed in terms of two components. The first component will be CT, and this is the zeroth component, and the first component will be VT in general. In the rest frame, it becomes a C tau 0. As we have already derived, the matrix elements for the Lorentz transformation that boost the particle from the rest frame to a moving frame, that is, in the rest frame it is fixed if the frame is moving backward, and in this frame this particle is moving forward, and the matrix elements are all positive, and diagonal elements will be gamma. Gamma is the Lorentz factor, 1 over 1 minus beta squared, and beta equals V over C. And off-diagonal elements are or equal to beta times gamma. We recall that the determinant of this matrix is gamma squared and gamma squared beta squared. Actually, from this, gamma squared equals 1 over 1 minus beta squared. So gamma squared 1 minus beta squared is always 1. Therefore, determinant of this matrix is always 1. Actually, this one shows that there is a length contraction and time dilation. The two effects cancel exactly in when we define the four-dimensional space that has time variation and spatial variation. If we find a product of this change in the space-time coordinates, then it is volume of a parallelepiped dimension described in the four-dimensional Minkowski space. And this product is actually invariant on the Lorentz transformation. This is a very, very important result. For example, on the rotation, three-dimensional spatial, the volume element is invariant on the rotation, something like that. This is a prime. And in four-dimensional space-time volume is invariant under Lorentz transformation. This one shows, this one is very similar to the fact that on the usual rotation is cosine, sine, minus sine, cosine. This determinant is cosine squared plus sine squared equals 1. However, in this case, determinant is this one product, this product subtracted by this one. That means the product is always 1. Or gamma squared minus the gamma beta squared equals 1. That means square subtracted by square is always 1. We can introduce a real parameter that satisfies this cosine hyperbolic function, any cosine hyperbolic function and any sine hyperbolic function with the same parameter always satisfy this identity. You can follow the analytic continuation from the cosine and sine to arrive at the cosine hyperbolic and sine hyperbolic. So the Lorentz transformation matrix is completely expressed in terms of a cosine hyperbolic and sine hyperbolic. This is, from this we can confirm the invariance of the scalar product of the four vectors defined in Minkowski space. The additional point we can find is we can factor this gamma out, then the matrix is diagonal element is 1 and this is beta. And actually, this is the ratio of sine and cosine hyperbolic function that is actually tangent hyperbolic function. Tangent hyperbolic function is V over C is scaled by tangent hyperbolic. As just like the rotation matrix, hyperbolic function parameterization for the Lorentz boost matrix can be multiplied, and we can apply the identities for summing cosine and sine hyperbolic function. Is very similar to the rotation matrix, except that this is hyperbolic functions. We can apply this to find the velocity addition formula. This is the final result for the velocity addition formula for boost by V1, and again along the same direction we boosted by V2, we reach V1 plus V2. However, there is a denominator with the V1, V2 over C squared. For example, if V is almost the same as speed of light, the result is, what's that? C plus C, 1 plus 1 equals C. You can boost up almost the speed of light and again boost by speed of light. What you get is not 2C, but still C. So speed of light is invariant in any reference frame. That's it for today.